Okay, so we're going to look at frictional forces, starting with data, and then we'll look at the math later. So here I have a force sensor. I'm going to use this force sensor along with a frictional block and some masses. We're going to see if putting different amounts of masses on the friction block or using the rough side versus the smooth side affects the amount of friction that the force sensor sees. That could be static friction or kinetic friction. We're also going to see the transition between the two, which would be really cool. So here we have the small amount of mass and the rough side of the block. So you see that static frictional force growing, and then, once we start moving, then we're engaging kinetic friction, which remains roughly constant. Interesting. And next up we have the small amount of mass and the smooth side. So you can see something very similar happening, except that transitional period seems a lot less pronounced, a lot smoother. Right. Now here we have a big amount of mass in the rough side. Luckily I was able to borrow this brick from Mrs. Armstrong's office. Okay, there's that transitional period. You can also kind of tell that the magnitude of both types of friction seem to be a little bit bigger the more mass we put on the block. You can't necessarily see the numbers very well in this video, but it does appear that both frictional forces have a larger magnitude. And this is the smooth side as well. You can see there's still that very smooth transition with the smooth side, no matter how much mass is on there. And here are just some other trials. So overall, you can kind of see the same basic thing seems to happen. The static friction force grows, and then kinetic frictional force is engaged once we've hit some kind of maximum value, and that kinetic frictional force remains about constant. And we can also kind of see that the amount of mass put on the block also seems to affect the magnitudes of both of these forces. So now let's look at the math. Okay, so now we're going to use the data that I gathered using those tools, and we're going to look at the graphs and try to sort of reason about whatever we can about the potential model, the mathematical model for how the force of friction, how this relates to sort of the mass or the weight on top, and how it relates to the particular side that we used, right? There was a smooth side and there was a rough side. Right, so the different sides actually had, showed us different things in the data. So I'm going to start with these two graphs. Remember, this portion of the graph was only gathering data when the mass was at rest. And when the mass is at rest, we typically say that this is static friction, right? When we say something's in static equilibrium, what we mean is not moving. Right? The mass is not moving. Whereas once static friction was over, we get what we call kinetic friction. When kinetic friction is engaged, the mass is moving. Right? So that's literally the only difference. It's more of a semantic thing, but they do have different relationships. Right? Static friction and kinetic friction have different models to them. So static friction, we say, is dynamic. It can change. Right? It can change according to whatever force is necessary to keep the mass at rest. So you can see, right, the magnitude of the force is changing a lot, right, in that short amount of time. Kinetic friction typically, does not change approximately, right? Obviously, you can see in this section of the graph, it is fluctuating a little bit, right? But more or less, if you were to do a least squares regression, it would fit the data pretty well, and it would have roughly a slope of 0, right? So there's a caveat here. Of course, it does change a little bit. There's tiny fluctuations, but if we were to approximate like ideal kinetic friction, like perfect kinetic friction, it wouldn't have any fluctuations in it whatsoever, right? But of course, the real world is messy. So we have static and kinetic friction. One changes, one doesn't change. We also notice too down here, right, there seems to be some sort of maximum magnitude for static friction. And the moment we go past that, we get like a little bump here. and that's when the kinetic friction sort of takes over and the mass starts to move, right? So we've sort of reached some sort of maximum value. And that seems to be pretty consistent in all the graphs too. There's a little bump. We pass this maximum value, the mass starts to move, and then the force sort of recorrects itself and then goes flat. So these two graphs are analyzing the force that the sensor reads, except the only thing we're changing is the amount of mass on top. Right, so the mass, if you remember, here's the friction block, and it was connected to, this is the force sensor right here, and it was connected to, this is the friction block, zoom in here. And so we had like kind of a rough side, and we had a smooth side, and we were pulling it to the right, just sort of on the track. So the force sensor was reading different things. And you can see both for, the soft side, the small mass situation, right? So when we had just, a few little things here. And then we also had a nice big old brick, courtesy of Sherry Armstrong. Right, so this is the big mass, right, small mass. Seems like both kinds of friction attained greater magnitudes when we had a bigger mass on top, right? So you can see the value that this maximum for static friction corresponds to. I guess if we had to guess, maybe this is around negative 7.4 newtons, right? Whereas if we go over here, seems like that maximum is attained around negative 4. We're just guesstimating here, but maybe negative 4.2 newtons. But clearly, it has a smaller magnitude. And the same goes for kinetic friction as well. So it seems like, just for friction in general, if we just call this F, it's friction, if the weight on top, the amount of mass goes up, then friction goes up. If the amount of mass on top goes down, the friction goes down. What else is changing too, by the way? So like when the mass on top goes up, we could also say that not only does the friction go up, but if you think about the free body diagram for the friction block, right? So it's having a applied force from the sensor, right? And the sensor is reading the third law pair of that force. It has a normal force going up, right, from the table. But that normal force is going to change based on how much mass is up here, right? So the mass is pushing down with some amount of force. So we could call this the force from the mass on the block. I know it's a really long name. And then, of course, the block also has some gravity to it as well. So maybe that looks like this. And so the normal force, depending on how much mass is on the block, is going to have to get bigger. Right? So if I had a situation where I had a lot more mass, M, then the force of the mass pushing down on the block would be a lot bigger. The force of gravity on the block would be the same. All right, so we would call this F, whoops, this was the green arrow. F of the mass on the block is a lot bigger. And so the corresponding normal force would also have to be a lot bigger too. Right? If you just think about the free body diagram, right? And we also observed, right, when the mass is a lot bigger, we have a bigger, observed force from the sensor. Again, because in both of these situations, there is the frictional force. We could just call it lowercase f. So in this case, it was a little bit bigger, right? and this is in equilibrium, right? So actually I kind of drew these a little bit too big. The applied force in this case was a lot smaller, and so was the friction. Right, so that seems to be what we're observing, right? So the point is the friction goes up and the normal force goes up. The normal force applied to the friction block. If the friction goes down, the normal force seems to go down, right? Okay, so that's one conclusion we can draw. We can also draw something by looking at the rough side, big and small mass. Again, you can kind of see we attain bigger maximums for the magnitudes of my forces, right? This is like around negative 3.2, whereas this is maybe around negative 6.7-ish. One thing we also see, though, is these little jumps here, right? So static friction and kinetic friction seem to have different sort of, I guess we could say, maximum magnitudes, right? Or different ways of interacting with the surface. And so there's these big old jumps here. So we'll explain that in a second. If we look at when we keep the mass constant and we switch the side, what seems to be different are these little transitional periods, right? So for smoother surfaces or smoother, if one of the surfaces is smoother or if they're both really smooth, there's a sort of smaller transition. And then if there is sort of a rough side, there's a bigger transition. So mathematically, one thing we can say is F static is always less than or equal to some maximum value, right? Whereas kinetic friction seems to be just sort of equal to some value. And that value seems to be tied to the normal force in some way, right? Because if I look at the segments where the mass is in motion on each graph, no matter if I'm using the rough or the smooth side, I get a different magnitude force based on how much mass is on top, right? And we said the bigger the mass, the bigger the normal force will be, right? This would give you a small normal force acting on the block, right? And so we end up with a smaller frictional force. So it turns out the mathematical models here, the size of the static frictional force is always going to be less than or equal to some sort of constant. Right? We'd say this is the Greek letter mu. Mu, something like that. Right? Not meow, mu. And we would say mu s. So this is what we call the coefficient of static friction. And I guess what we could do to figure that out is if we were to graph the force of friction here, and if we were to graph the normal force, we could actually use the slope to find mu. But that's maybe for another time. So it's the coefficient of static friction times the size of the normal force. So there is kind of a linear relationship between the max value of static friction and the normal force. And the slope there is mu. Whereas kinetic friction has its own constant. We would say this is mu k. Now you might be wondering, well, if it's the same surface, right, can't I just say that mu s equals mu k? Well, here's the problem, right? These jumps. Right? These jumps are essentially telling you that mu s cannot equal mu k. Right? There are different coefficients once you have one form of friction versus the other. Because all that's happening here, if you think about it, is I'm just pulling at this transitional period, I'm pulling with maybe 0.01 newtons more of force. And the moment the mass moves just a little bit, the frictional force jumps down a lot, right? So essentially the idea is the normal force has remained constant, the surfaces are the same, but we're getting an incredibly different value for the frictional force. And so actually, in most cases, these are not equal to each other. So the kinetic frictional force, these don't have to be don't have to be the same. Right, this and this. They could be totally different values for the same surface, but it's still the same kind of relationship, right? It depends on how much weight is on top, and that therefore changes the amount of normal force, right? More normal force means more friction. And so we have a very similar relationship. Now, I wasn't able to derive all the details of this straight from the graph, but hopefully you can see why this model makes sense of the data, right? It makes sense of these graphs here, right? It makes sense of the transitional points. It makes sense for why the force changes in the first part and stays the same in the other, right? It's because of this inequality is sort of at play here, right? We're increasing the force until we reach some maximum value, right? So I hope these make sense, and let's go ahead and just do some problems here real quick with it. So, very typical problem. You guys have actually already done this a little bit. You just haven't done it as detailed in this way. Let's say I have a car. It's a very bad looking car. That's moving to the right at 50 meters per second. And it weighs 500 kilograms. Let's say that the coefficient of kinetic friction between the tires and the road, we call that mu k, is going to be 0.5. Now remember, mu k and mu s could be totally different for any two combinations of surfaces. They could be totally different numbers for every single different pairings of objects, right? So you have to be specific about what mu k is referring to, the tires and the road. Right. So the question is, okay, if I slam on the brakes, how far do I drift? How far do I drift until the car is at rest? And there we go. Let's start on it, right? So we know that in order to find this distance, right, we're going to need the acceleration of the car, right? If we have the acceleration of the car, essentially what we have here is V final. If it's at rest, or no, sorry, this is V final, my bad. This is V0, right? We have initial velocity and final velocity. We're looking for displacement, and we want, if we can find an acceleration, we could put all this together in one of our kinematics, right? You guys have actually done this, I think, a few times, but only in a kinematics-based problem, not with force at all. Okay, and you know what we could do too, before we even deal with forces at all, we might want to go ahead and just solve for displacement, and that way, once we find the acceleration, we can just plug it in all the other values. All right, so if you solve this algebraically, I'm not going to show all the steps here just for time, but you should end up with something like this, right? So I subtracted V naught squared from both sides, and I divided by 2a. All right, so let's try to find all this stuff here. So the main thing is, what is the acceleration of the car? What do we always start with once forces are involved? Newton's second law, right? Acceleration of the car equals the sum of the forces over the mass of the car. There we go. And we're concerned with the forces in the x direction, right? There is no acceleration in the y direction. So the only force acting on this car is the force of friction, right? We slammed on the brakes, and there's just kinetic friction, right, going to the left. Well, I guess technically speaking, there is the normal force, of course. In fact, it actually should be bigger than the force of friction. Force, normal force. And then the force of gravity cancels it out, right? That's why the car is not accelerating upward or downward, right? But it is accelerating horizontally, right, to the left. The acceleration is to the left. So this is going to be negative force of kinetic friction divided by, we said it was 500 kilograms. And how do we calculate this? Well, kinetic friction is negative mu k times the size of the normal force, using absolute value bars there, divided by 500. Well, we know what mu k is. I told you that was negative 0.5. Now, how do I find the normal force? Well, we know because we're balanced in the y direction, this normal force has the same magnitude as the force of gravity. We can calculate that pretty easily, right? It's going to be 500 kilograms. Or sorry, 5,000 newtons. Right? If you take 500 kilograms times 10 meters per second squared, that's the force of gravity, that should be equal to the normal force there. And then divided by 500. Now it turns out, looks like we end up with negative 0.5 times 10. So this equals negative 5 meters per second squared. Isn't that interesting? Okay, so now, go back to our equation. Let's start putting some stuff in, right? So VF squared is 0. V naught squared is 50 squared divided by 2 times negative 5. So I get negative 2,500 divided by negative 10. So I get a positive number here, 250 meters. That's a lot of meters. Right? Think of 250 meter sticks all lined up. Now, to be fair to us, right, we had a pretty fast speed, and this is a pretty heavy car, right? So it has a lot of, I guess all we can say now is like inertia or something like that. We'll talk about momentum later, but essentially what's going on here is that even though our gravitational force was 5,000 newtons, our frictional force was 2,500, because essentially what happened is this coefficient of kinetic friction cut it in half, right? And the lower this goes, the lower our force of friction is going to go. And essentially, all we can really say about these coefficients, right, static or kinetic, is that they're essentially not going to be equal to 0, because there's always going to be some amount of friction in the world. So there's always going to be some number bigger than 0. Typically, they're less than 1, but they can be bigger than 1, I guess, maybe in some cases. But I haven't seen an example. So I guess essentially all we can really say is typically, I'll just say typically, I don't know for sure actually, that these values are between 0 and 1. They're coefficients. Okay, so here we have sort of a combination of kinematics and Newton's second law, and that's something that the AP people love to do, is they combine forces with kinematics, and you sort of have to pair them together. But now you're kind of just solving a little bit more complex problem, and you're just doing Newton's second law for one part of it, and then you're using a kinematic for the other. So, kind of interesting. Here's maybe another example. Let's forget about cars for a second. So here, we're pushing a crate. And the crate weighs 30 kilograms. And let's suppose it takes 100 newtons to get the crate to start moving. And the question is, what is mu s? And yes, we can actually find the coefficient of static friction here. Okay, so why do they mention this detail, that it gets the crate to start moving? Why is that important? It's because once the crate starts to move, we have hit the maximum value. We've hit the maximum value of the static frictional force, right? So in essence, equation-wise, what this tells us is that the static frictional force is now equal to mu s times the normal force. And that's important that it's equal, because otherwise we wouldn't really be able to solve for mu s. All right, so I guess all we can say right now is, okay, this coefficient of static friction equals the force of static friction divided by Fn. Interesting. Okay, let's keep going. What do we do now? Well, here's maybe another good place to start too if you're ever lost. Draw a free body diagram. You know, once you've done it 100 times, you can do it another time without really thinking too much. So, okay, here's the crate. It's a dot. I know that we're going to have a normal force, maybe like this. And I also know that the force of gravity is going to be equal and opposite. Okay. And I'm pushing on it with 100 newtons. So maybe like this, 100 newtons this way. We could call that an applied force. And I also know that there is static friction resisting me, right? But if we're about to start moving, but we haven't quite gotten there yet, you want to think of this as this is the moment just before motion. Meaning that the mass is at rest. Right, we're thinking of like 1 millisecond before the crate starts moving. We actually have a balanced force diagram here. And so actually what we can say is the magnitude of the force of static friction is 100. Right? That's the only way this situation is balanced. And that the normal force is equal to the force of gravity, which we can calculate pretty easily. Right? So that's going to be, looks like 300. And so my coefficient of static friction looks like is like 1/3, or about 0.333 repeating. Interesting. So the coefficient of static friction is actually pretty easy to calculate, it seems. Right? You just take the amount of force required to get the object going, and then you just divide by, well, even without even thinking about normal force, we're essentially dividing by the force of gravity of the object. Now, that's not always going to be the case. If we were to put maybe another weight on top of here, like 20 kilograms, well, then there's going to be a third force in our free body diagram, right? And then this force will adjust. But if it's this simple, then we don't need to worry about that. So this is essentially how people come up with these coefficients, right? It's interesting. So there's force of static friction to get it going, divided by force of gravity. And lastly, let's see, what other space do I have? Let's maybe do it below this graph here. Let's do one that doesn't involve sort of any numbers, because you will see problems like this on the AP test. In fact, let's do one that involves a spring. Oh man. Yep, I'm doing it. Okay, so that's a hand. All right, so the idea is the hand is sort of pulling this spring to the right. Since the spring stretches, it stretches a little bit. All right, so this is like LEQ. And let's say it stretched this much. So we'll call that delta X. And, let's say this is also when the mass is just about to move. All right. So we have static friction engaged here. And the question is, solve for the spring constant K in terms of all other physical quantities. Cool. So there's a spring constant K, and we also have some kind of coefficient of static friction that we'll call mu s. So, okay, this looks like a very complicated problem, but just take it one step at a time. That's the best way to do physics. What is the next right thing to do? Well, I know that there's forces involved. So a good starting point would probably be maybe some free body diagram. Let's draw all the forces for the mass. Okay, well, it's just about to move, right? But it's at rest. So this free body diagram should be balanced. I know that. Okay, what else do I know? I know that the surface is pushing up on the mass with some normal force. I also know that the force of gravity is pulling it down, and those should be equal and opposite because we have a balanced diagram. We already figured that out. I know that there's a spring attached on the right side, so there's some kind of spring force pulling to the right. I can't put Fs here. I guess I can. This is capital F, but maybe I'll write out spring. F of the spring. And that if we're at rest, there must be an equal and opposite force going the other way, and that is the static friction. I'll put F stat going that way. These must be balanced. Okay. So what does this mean? Well, what we can do is maybe we can start using Newton's second law. We can use it on the x direction and on the y direction. So that's another good thing that we can do. Right, that will at least give us some equations and some relationships. So the acceleration in the x direction equals the sum of the forces in the x direction divided by the mass. Well, we know that the acceleration is 0, and the forces are the force of the spring, which is a positive force, minus F stat. And this is divided by the mass. Okay, we know that mu s is going to show up there, so how about we keep going with this equation? Well, the force of the spring is going to be K times delta x, right? In fact, let's do one quick thing to make this even simpler. Multiply by m on both sides. Get rid of that. This turns into 0 anyway. So we get 0 equals K times delta x minus, this will be mu s times the normal force. Now, how do I know it's equal to that? Well, it's because we are just about to move, right? We've basically, again, we've hit the maximum value for static kinetic friction, right? So it's equal now. And we're solving for the spring constant. So actually this equation gives us that, right? If we solve for K, we should have mu s times the normal force divided by delta x. Oh, and we can find the normal force, right? Because vertically we are also balanced too. So the normal force should be equal to the force of gravity. So this would be mu s times the force of gravity on the object, which is just m times g. So here's the relationship. K equals mu s times mg divided by delta x. This is what we call functional dependence. Now, for a spring, the spring constant is what it is. It's not going to magically change, right? But what this is saying is, if we were to observe a different trial of the same thing using a different spring, it would have a different stretch length. This would be the same. Let's say this is the same. and this is the same. And so it would have a different spring constant, right? Or if any of these other quantities were to be different, we would be observing a different spring that would be either stiffer or looser, right? So like, let's play around with this. If the mass increased, then looks like K would increase too. Does that make sense? Well, if the mass was bigger, that would mean a higher normal force, bigger normal force, which would mean a bigger static frictional force, which would mean a bigger, hold on, my arrows are getting a little confusing here, which would mean we would have to have a bigger spring force, right? And so the only way for that to happen, if delta x is constant, the stretch length is constant, is for this to increase. Right, so this functional dependence is a little bit more complicated because a lot of these, we have sort of three quantities that can all change, and it's a little hard to visualize how they can change. But anyway, this is the relationship. Back when I was at Georgia Tech, my professors would actually do this all the time, and it would really frustrate me. And I actually didn't have an appreciation for it until like a year later. But this is actually a much more powerful way to solve physics problems. Because if you get one of the numbers wrong, all you have to do is just change the new number that you got wrong, that maybe you plugged in the wrong number. You have a formula and you just plug in the new number or the correct number, right? Whereas if you plug in the numbers first and then you do all this algebra over here and you get to the wrong answer and you realize you plugged in the wrong number at the very beginning, like maybe down here, well, now you got to redo all that algebra again, right? But if you have the formula, the algebra is done, right? So if you get one of the numbers wrong, no worries, right? Just plug in the correct value. So anyway, I hope this helped. Hope this kind of gives you an understanding for why these relationships are what they are, right? So we'll do more problems with friction in the future.